Q factors. Here we go, Q factors. Alright. Q factor is a property of a coil, and when dealing with resonant circuits, the whole circuit itself can have a Q factor. But it must be specified for a frequency. It's good for, or a range of frequencies in a bandwidth. It's BW, bandwidth. But the Q factor, whenever you see these L here, that means of the Q of your coil. It increases with frequency to a peak and then decreases due to the skin effect and the self-capacitance of the coil windings. So there is your Q factor. It's going to go up as your frequency goes up, and then it's going to peak and start to drop off because of your skin effect. That means just the outer part of the conductor is going to have your current through it, which is why we use copper pipe when building Tesla coil primaries, because only that outer part of towards the circumference of the material is used. You can use solid wire, you just won't use all of it at Tesla coil frequencies, say 100 to 250, maybe even 300 kilohertz, but sometimes it drops off at megahertz. It varies. The Q factor of a coil, L, there's our schematic symbol, is going to be X sub L, the reactance of the coil, over R sub L, where R sub L is you take an ohm meter and you read the ohms off of the coil, literally treating the coil as if it was a resistor. That's R, your resistance of sub L, which equals, well, the current through the coil squared times X sub L, and current through the coil squared times R sub L, which would mean the power, remember I squared R is power through the resistor, and power on the coil, but because of math, the current squared cancels out, and we can just use XL over R. This is Q sub L, or this, you often see it as Q lowercase l, cursive. Q sub L, lowercase. Sometimes sub L means your load, so to keep it simple, a lot of the time I figured out while I was taking the class that, oh, that's why he uses lowercase l sometimes. So you get used to writing in cursive and Q sub L. Yeah. Q factor is a ratio of the reactive power of the coil to the average power dissipated in the coil's resistance. This is a reactive power on your y-axis to the resistive power dissipated, treating it as a resistor on the x-axis. So here we have R sub L. Because of the algebraic property of when you see something like this, if we want to solve for R sub L, then that is just XL over the Q sub coil. And if we know the R sub L, and we know the Q factor of the coil, then we can find the reactance of the coil, X sub L, by multiplying RL and QL, because math. So of a series resonant circuit, it has a Q factor. QS for series is XL over R equals omega S for series times L over R, because X sub L equals omega S times L. I guess, remember, is 1 over square root of L times C. Or, well, or an easier way to think of it is omega S. Omega is 2 pi times your frequency in this context, not radians per second, but think of it as 2 pi F times L, because that is your equivalent of X sub L. Remember, when you have the same symbol, meaning more than one possible outcome, look at the greater context of which it's being used. Omega in this context is exabel, so it must mean 2 pi f times L over the R being any resistance in the circuit, including the resistance of the coil itself. And another funny property that you get to with some more fiddling around with the math is the Q factor equals 1 over R times the square root of L over C. So there's more than one way to get there. It's a good way to double check your work. So for series RLC and communication circuits, Q factor is usually going to be greater than 1, preferably 10 or more, depending on how much bandwidth you want. So R is your total circuit resistance, not including the reactance. So this R, when you account for this R, this is just DC resistance. This is not reactance. So Q factor and bandwidth. So I was just referring to bandwidth and Q factor are definitely related. So see, when you think of bandwidth, you think here is the width of your band. So here, let's say we have current, and let's say this is how much current is through our circuit over time, our series circuit, and it will go up and it will peak at F sub S, our series resonant frequency here, and then it'll drop back down as we drop out of resonance. So this is the resonant circuit. So our current comes up, it goes to a peak and goes down. But if you look just straight across, this is a 0.707 times our current. And this is as our frequency increases. We have F sub 1 and F sub 2. F1 and F2 are the boundaries of our bandwidth. So the selectivity is the width of the distance between F1 and F2. Is our frequency range. This is the width of our band. This is our bandwidth, literally. So the higher the Q factor, the narrower it's going to be, and the sharper the curve. Imagine it going up like this. If it were to come up and peak and then drop down suddenly. So band frequencies are 0.707 times your max current, and I is always your voltage source over your resistance. So it's F1 minus F2, which is equal to R over 2 pi L, which is equal to F sub S, your series resonant frequency, over your Q factor, equals or if you have a parallel RLC circuit, then it's the frequency parallel over the Q of your parallel circuits. If the Q factor is greater than 10, then it's pretty much going to be split in half one way or the other. So that means your frequency 2 is going to be equal to this frequency plus half of your bandwidth over 2, it's half of it. And your F sub 1 is going to be this minus, going to the left is minus, bandwidth over 2. Is bandwidth. So at 0.707, getting back a little more into that, that is what we call a half power frequency. So at the cutoff frequencies, F1 and F2, the power total, your volts times your amps, is going to be 1/2 of your I squared R, or V times I, or V squared over R, any method of getting power. Example, and there's an example, if say your max current is 5 amps and your resistance is 2 ohms in your coil, and your half power frequency is, well, the power at the half power frequencies is of F1 and F2 exactly is going to be, say, 5 squared times 2, it's going to be 25 watts. So that can be, say, for example, your minimum power, and anything over that power will go through your say, your transistor or your circuit, if it's going to be a current-sensitive device or what have you. There's your half-power frequencies. And here's Q of a parallel resonant circuit. So this, when you have a parallel element, then new clip. For parallel resonance, your Q factor is R over XLP, which is your series resistor in parallel with your, you add another parallel resistor with some math. It's still a ratio of reactive power over dissipated power. If your Q factor is less than 10 for your coil, then you want to convert your parallel resonance circuit here. So here's your current source, here's your source resistor to make a nice little Norton current source. So R sub S should be pretty high. And then when you think of an inductor, it's really, you can think of it as the resistance of the inductor being in series with the actual inductor itself. And then you get your capacitor. You want to convert R sub L to R sub P. So to bring this, because here we have, it's a little messy having parallel and then two elements in series and then just a parallel item. We want to bring this R sub L down so it's parallel resistor, coil by itself, and then capacitor, thankfully, can just be by itself as well. So there's an equation we use to convert R sub L to R sub P over here, and another equation we use to convert the reactance of this coil to the reactance of this coil over here. And those equations are the same sum in the numerator. XL parallel is RL squared plus XL squared over X sub L. So in order to do this, you need to know what frequency you're operating at, because, of course, X sub L equals 2 pi FL. And then our parallel, this little R sub L, you take RL squared plus XL squared, divide that by R sub L. Now we can put this R parallel up over here in parallel with the source resistor, solve that down, product over sum to get two resistors in parallel, get total, treat it as one resistor. Then we can solve for XLP, XL and parallel, and then, well, at resonance, XLP equals X sub C. Those two would cancel out. Our total impedance is just the RS in parallel with R sub P, which here's RS in parallel with R sub P divided by RXLP, and that is the Q factor of the parallel resonant circuit. More involved than series. The math, as you see, there's a bit more to it, but all we're doing is just squaring and adding the result of the squares, and then just dividing it by X sub L. The math, each step of the math is not that hard to do, but you just got to remember to do each step properly. Take your time, pace yourself, get your numbers right, and then you'll select the right components, and it'll be less expensive to actually build a unit that's more likely to work right first time. RLC parallel Q at resonance. Right, this is just another way of looking at that previous card. Q is, again, always the reactive power over your dissipated power. It's that ratio. And let's say another way to think of it as Q parallel equals R over your XLP. Remember, not just XL, but XLP. But because these VC squareds cancel out and these XLP and R flip there. So R is your source resistor in parallel, so R, and the product over sum. So that should cover you on RLC parallel Q factors, RLC parallel resonant frequency. Again, if the Q is less than 10, we got to do a little bit more math to get there. To bring this closer here, Q is less than 10, and it's the same formula, 1 over 2 pi square root of LC, but you also multiply that value by 1 minus this whole deal here. So you take R sub L, you square it, you multiply that by the capacitance in farads, and you take that product and you divide it by the inductance of your RLC circuit. Even if R is just the resistance of the coil and all you have is a coil and capacitor, you can still get your parallel resonant frequency. So first, take the product, then you multiply, then you divide, and you take that value and you take 1 minus that value. Then you take the square root of it. You got to do all of those steps and take that final product, here, that final square root, and multiply it by this formula, your standard series resonant value. So it's a little bit more involved, there's more steps, but the actual individual steps themselves are not that hard to do. So just, again, go slow, pace yourself, and you'll get the right answer. If Q is greater than or equal to 10, then you can just use the series resonant formula. That's usually sufficient, as I mentioned. Multiplication factor accounts for the RL and the X sub L in series transformed to RP and XLP to make a completely parallel circuit, as we just reviewed on our previous cards. So the parallel, well, when you're dealing with parallel resonant circuits, here we have this max impedance frequency, which is basically the same formula that we just looked at, but 1 minus 1/4 of that value, R sub L, here I use the cursive, as you should too, lowercase l. FM is where max impedance, Z max, occurs, and F sub M is a little higher than F sub P. It's only 1/4 of that value here. So F sub P, parallel resonant frequency, is for a power factor of 1. F sub M, if you want max impedance conditions, is from this formula here, 1/4 of it. And that's the frequency at which you will have max impedance. And the F sub S is for your series resonant circuit if you have a really good coil with a really high Q factor, greater than 10, based on your LMC values. So a standard parallel for unity power factor and greatest impedance, or just series equivalent.